In this video, we will be looking at the KKT conditions for the support vector machine. The SVM can be either written down in its primal formulation or the dual formulation. So a big question here is how are these two formulations connected and why are they giving out the same solution? The answer is a KKT condition. Then the second reason we want to look at KKT is to see how the support vector appears in the SVM. So using the KKT, we will be seeing why most of the data points are not support vectors. Only few data points become the support vectors. That is important to the decision boundaries for SVM. Okay, so let's get started. So first, let's talk about KKT conditions in general as an property for the optimization problem. So suppose we are given this constraint optimization problem in here. We want to minimize function f of x with respect to x. Then we also have the constraint of g of x greater or equals to 0. So that is the general optimization problem that can lead to the KKT conditions. So actually, there's a very nice geometrical way to understand KKT. The intuition is that the solution, the optimal solution, can either lies in the interior or the boundary of this constraint. Okay, so let me just give you a few examples here. We'll be looking at 4 different examples. The first one is going to be very easy. It's just going to be the unconstrained problem. The first example here, we just consider the unconstrained problem. Suppose we're just going to ignore the g of x constraint in here. Then that's really an easy problem, right? If you just want to minimize the function f of x, then we just set its gradient equals to 0, right? So that is the easiest case. But in here, I should also emphasize that we're just going to make the assumption that f of x and g of x are both convex. It's a convex optimization problem that we are facing, right? That's going to simplify our life a lot. Then what happens if we add a constraint to it? Well, that gives us a second example here. Okay, then for the second example here, let's consider the constraint problem. But here, for the first situation, let's consider that the optimal solution is in the interior. So this is a plot we're going to look at, right? So we have the same function f of x, but now we also have a constraint that g of x is greater or equals to 0. So that is the constraint we are dealing with, meaning that we can only find the optimal solutions within this region. So suppose the solution is interior, then that really doesn't change much from the unconstrained problem, right? Because we can still set the gradient equals to 0. But also that means our constraint need to be satisfied, right? This g of x star need to be smaller than 0. That means the optimal solution lies in the interior of this constraint. Well, that's really the second case. The next one we're going to be looking at this most interesting one is that we have a constraint problem, but the solution lies in the boundary of this problem. And for the third example here, this is the most interesting one. So what happens if the solution lies in the boundary of the problem? So suppose we are given the same function f of x, but our constraint is given by this, right? It's given by this region here. So see that the optimal x star value that minimizes the function f of x is not the same as the global minimizer for the function f of x, right? So here, right, you see the global optimal is in this place, but that is outside of the constraint. So in this case, it turns out that our optimal solution has to lie exactly as a boundary for this constraint, right? So that is the most interesting case. And actually for here, we have to consider the multi-dimensional case. So I also draw the picture for the multi-dimensional case. We're going to look at that instead of the 1D case. So let me just grab those together, right? So this is going to be the picture we're interested in, right? So this is actually the same picture as the Lagrangian multiplier. Okay, now let me explain this picture in here. So the red circle here is a constraint g of x. So what this means is that our feasible x can only lies within this constraint, right? It can lies only inside this circle. It cannot go outside when we are doing optimization. Then this function f here is actually the contour line. So this is a contour of x, right? So see that I'm drawing the gradient vector in this, sorry, I'm drawing the negative gradient vector in this direction. So what it means is that if we travel along this direction here, the function value increases. And I can say that this point here is the global optimum. So that's going to be f of x star global. We'll see that the problem here is that this global optimum really lies outside of our interested our constraint region, right? Um, so it turns out that in order for this to reach the optimal, the gradient vector of the g has to be in the same direction as the gradient vector of the f, right? So that's a property of the Lagrangian multiplier. So this makes perfect sense, right? Because if we are living in some other places, let's say if we are living in some other places, then this contour line, if we just keep drawing this contour line, it means that the value has to be smaller than the contour line when they are tangent to each other, right? So the important thing is that the contour of x of f is tangent to to the to the boundary to the constraint g of x. Okay, so that gave us the Lagrangian multiplier for this particular example in here. So if we write down this in terms of the equations, it means that there need to be two equations satisfied, right? The first is that g of x star needs to be zero, right? So this means that the boundary is activated. Right, so I should say that this particular point right here is our x star. So the boundary needs to be activated. Our optimal is exactly at the boundary. Then the second one um, is that the gradient vector of the function f has to be in the same direction as the gradient vector of the function g. So this equals to zero, right? This is a Lagrangian multiplier. So for the idea of the KKT conditions, it's really a way to combine these two situations into one framework, right? So if we just combine these two together, that gives us a KKT condition. So a trick that we can use here is that for this interior solution here, we can introduce a multiplier variable. We can use in the same variable lambda into here, right? So we can introduce a lambda parameter into here, but setting lambda equals to zero. We can actually augment this first equation here by adding a lambda times the gradient of g x star, right, equals to zero because lambda equals to zero in this case. So that is really the idea of the KKT conditions. Let me just start a new page to written it down. Okay, so now let's write down the KKT conditions. There are in total of four conditions. So the first one we're gonna do is complementary slackness. So it can be written down in this way, right? We can write it as lambda times the g of x star equals to zero. Okay, let me just combine this with the second condition to explain them together. So the second condition is going to be the stationarity condition. Right, so we have this second one. So the second one is just going to be the same as the Lagrangian multiplier plus lambda equals to zero, right? So let's just combine these two conditions together to see what it means, right? So for the complementary slackness, you see that there are really two cases, right? The case one is going to be lambda equals to zero, right? So when lambda equals to zero, this means that the case one in here is that the gradient of x equals to zero, right? Because the second term goes away. This is the interior case. Then the case two for the complementary slackness is that the g of x star equals to zero, right? So this is the case when the solution lies in the boundary. Then for the stationary condition, the case two is just going to give us the exact same as the Lagrangian multiplier, right? X star plus lambda g x star equals to zero, right? This means that the optimum lies in the boundary. Right, so that is the key idea for the KKT conditions. Then we have two more conditions for KKT. They are relatively easier to understand. The third one is primal feasibility. It says that the g of x star has to be greater or equal to zero, right? So that is just the constraint for our primal problem. And the fourth one is a dual feasibility. In here, we'll have the lambda greater or equal to zero. So for the first one, you can actually see it from this picture in here, right? From this 2D picture in here, that because we are in this particular problem, right? So the negative gradient pointing in this direction, then the gradient of g pointing in the other direction, right? So when we combine them together, this means that lambda is greater or equals than zero. So that's the fourth condition for the KKT. Okay, I think I made a terrible mistake in here. So this multiplier, the sign of the multiplier should be negative. This is not positive. This is negative. Right, to see this, if we just move this term to the other side, it means that the gradient of f and gradient of g are in the same direction, right? I was confused in here because this is the negative gradient I'm plotting in here. So that is an important clarification. In here, it also should be minus. There we go. Okay, so now before we get into the SVM, let's look at how we can derive the duality, right? How can we show that the primal formulation for the optimization is the same as the dual formulation for the optimization, right? So this is called a strong duality. And this strong duality is not specific to the SVM problem. It's quite general. So let's just take a look at that, and then we can just apply this whole framework onto the SVM problem to do some interpretations. Okay, so now let's take a look at how KKT conditions implied the strong duality for optimization problem. It simply means that minimize the primal problem is equivalent as maximize the dual problem. So first we need to understand what is a dual problem, right? So this is our primal problem, right? We want to find the minimum for the function f of x given constraint g of x. So the first thing that we can write out is a bridge. This bridge is a Lagrangian. So for the Lagrangian, we're just going to combine the function f and g together. We'll have x and lambda as parameters equals to f of x minus lambda times g of x. Here the feasibility, the dual feasibility says that lambda needs to be greater or equals to zero. So this is kind of like the penalty or the lower bound for the function f of x, right? Because you see this second term here. So this term here is greater or equals than zero, right? So which implies that the whole function here is actually smaller or equal to f of x, right? So this is a Lagrangian. Then we can actually take the gradient of this Lagrangian to see what it gives us, right? So if we take the gradient with respect to x, that gives us the gradient of f of x minus lambda gradient of g of x. So see this equation is very nice, right? This is just like the stationarity conditions for the KKT and also the Lagrangian multiplier. So we should set this one to 0. But one thing to be considered here is that we also have the parameter lambda here, right? So when we set this to 0, we should actually set x star of lambda. So that's going to be the optimal. And how to interpret this is that we can consider lambda as a fixed parameter, right? For this, for here, right? For basically means that for a given lambda, we can have an optimal x star for it, right? So that's why x star is a function of lambda that's satisfied the gradient of f x star of lambda minus lambda times g x star of lambda equals to 0. So this is kind of the minimizer of L given lambda. Right. So suppose we set lambda as a fixed value, we can find the minimizer of that and define it as a x star of lambda. Okay, so the next step that we can do here is that we can actually plug in this x star back into the Lagrangian to see what happens. So let's do that. So if we just plug this in back into the Lagrangian, we will have so plug in x star lambda into L x lambda, right? So here we can actually define this as a new function. Okay, now we will be having a function with respect to lambda because we swap out the x. Let's call it q lambda. That equals to L x star of lambda. Lambda equals to f x star of lambda minus lambda g x star of lambda. So this becomes the very definition of the dual function. So sometimes the q lambda, the dual problem, is also written down in this way. It is a minimum of L with respect to x, right? So x lambda. Okay, so that is the dual function. And then for the dual problem here, we should just add a constraint to it. Okay, but first let's take a look of why we want to maximize this q lambda here, right? So that is the key. So why do we want to maximize this? So remember that our Lagrangian here is a lower bound, right? So it means that this function needs to be smaller or equal to f of x star of lambda, right? Then I'm saying that this equality condition can hold, right? For this inequality here, the equality hold exactly at lambda star. So this is the key, right? The equality hold at lambda star. All right, so see here, because the second term is positive, and when we set that to 0, it's the same as the complementary slackness for the KKT, right? So the complementary slackness of the KKT is saying that lambda star times g x star of lambda star equals to 0. So this implies that because the second term equals to 0, so you have q of lambda star equals to f x star lambda star, right? So this lambda star is a maximizer. of this problem. That is implied by the complementary slackness of the KKT. Okay, now let me just written down everything a little bit tightly. For the dual problem in here, right? Because we also have the constraints that we didn't mention here, right? So let me just clear up for next page. Okay, so here is the picture. We started with the primal problem of minimizing function f of x such that g of x greater or equals to 0. Then we write down the Lagrangian by introducing this multiplier. So that gives us a lower bound for the function f of x. So this is also called a weak duality. So this is a weak duality. Right, then we use the stationary condition to write out the dual function. So we found the minimizer for the variable x, and then we just plug in the lambda to get the dual function here. So this in this step here, that means that the stationarity of KKT is already checked. Then we also want to use then in here we also have the dual feasibility, right, as a constraint for this problem. I will say here is a primal feasibility. And finally, we want to use the last property of the KKT, the complementary slackness. It gives us Q of lambda star equals to f of x lambda star, right? This is a maximizer. Lambda star is a maximizer for the dual problem. So this condition holds when if complementary slackness is satisfied. And this is the strong duality we were talking about. This is a strong duality. So it just means that when we have a primal problem, optimization problem to minimize function f of x, we can just solve the dual problem by maximizing the function q of lambda. Then after we get a maximizer for the lambda star, we can also get the x star, right? Because these two are connected. That is a strong duality. So we should also show that the whole process here can be derived using the KKT conditions, which has that very nice geometrical properties for the constraint optimization problem, right? So all of the four KKT conditions are satisfied throughout these derivations in here. Okay, now it's time to apply everything we see into the SVM to see what KKT conditions can help us with interpreting the support vectors. So we remember that we started with a primal problem of the SVM in this form. This is defined on the feature space. This occurs in the feature space phi of x, right? That's our feature space. Then we write down the Lagrangian for this problem, and then we can define the dual problem in this way, right? By using the minimizer of x, we obtain the dual problem. Okay, now let me just also write down the KKT conditions for the SVM to see what happens here. So the KKT conditions. So note here we already have two KKT conditions, right? So this is a primal feasibility. And here is a dual feasibility, right? Right, so I'm not going to write these two conditions down once more, right? There are four conditions. I'm just going to write the other two conditions, right? So the first one is stationarity. So for the stationarity, we have the derivative equals to 0, right? So you have the gradient of L with respect to W equals to 0, and then the gradient of L with respect to B equals to 0, right? So we actually did the algebra for that last time, but it's not very hard to do, right? We just take the derivative. The first one will have W, the weight vector, equals to the a linear combination of the data points, right? Alpha I, yi, and then thing is phi of xi, right? So this is then we also have another one is the summation of alpha I yi equals to 0. So also the first one is very interesting, right? It means that the vector W lives in the span of the training data points in the feature space. So that is given by the KKT condition, the stationarity condition of the KKT. This leads to the kernel trick. So the second one is going to be the complementary slackness. It means that the multiplier alpha I times the constraint equals to 0, right? The constraint is yi W transpose phi xi plus b minus 1 equals to 0, right? So this is a complementary slackness. It can mean there are two cases, right? So the case one is that alpha I equals to 0. And then the case two is that the boundary, right, the constraint. And here, because I goes from 1 to n, right, so that means for each data points, we have a corresponding complementary slackness condition need to be held, right? So I goes from 1 to n, right? It means that for each data point, either the alpha I equals to 0 or the constraint equals to 0. So let me just draw it, all right? So see, like, what does it mean geometrically on the feature space? This is very important. Okay, so let me just draw our feature space here and with some data points. Then we also have the other class. Right, this is the decision boundary, suppose phi, and then our feature space is phi of x. We also have the margins, right, in this way. So here you see that when second condition holds, right? When second condition holds, what does it mean? It means that the data points lies exactly as a boundary, right? It must lies exactly as a boundary. So for these 4 points, right? These 4 points, that's the case 2. So if we take the dot product between the W vector and the vector of the data points, right? So this is going to be the phi of x. Let's say this point is x1, right? So we take the dot product between the two. That's going to give us a projection, right? Here let's just ignore the parameter b here. That's not very important, right? So once we take the projection, this projection equals to 1. So it means that it's lies exactly as a margin. There are points if the case 2 holds. And then for the other points, right? For these 2 points, for these 4 points, so there are these 4 points here, right? So that is the case 1. Right, so for these points alpha, the corresponding alpha equals to 0 for these 4 points. So what this means is that remember that our function, right, our final function can be written down in this way as alpha at the summation of alpha I k x xi plus b, right? So the decision boundary is that when we set this thing equals to 0, right? So that's the decision boundary. So the corresponding alpha for these data points equals to 0 simply means that these data points plays no roles in the classifier, right? They have no place in the decision boundary and the function f of x, right? So that's why our SVM is very sparse, right? So SVM parameters are sparse. It means that only the points lies at this boundary have non-zero parameters, right? Have non-zero weight parameters alpha. And for the other points, they are far away from the decision boundary. They play no role in the classification model. So this is an important interpretation of the SVM. So we call this vector support vector for the uh, for those in the case 2, right? These are the support vectors. That is the more important case to the SVM classifier, these data points. Okay, so that's pretty much about this video. We've shown that the KKT conditions kind of hold together the primal problem and the dual problem for the SVM, where the primal problem is defined in the feature space. The dual problem gave us a kernel trick. Then we also use the complementary slackness condition of the KKT to show that only some points that's exactly at the margin contribute to the classification model for the SVM. So that is a very interesting property of it as a result of the KKT.